What is it? You can't what? You can't see?
Hello and welcome. Thank you for coming out. My name is Donforth. I'm a lecturer up at the University of Vermont in the physics department. Hopefully you've had a chance to play with some of the hands-on demonstrations. If not, they'll still be here after this show. But we're here to talk about something that all the Vermonters really know, which is cold, right? So here in Vermont we get nice and brisk on occasion, but we're going to talk about things that are a little bit colder. The stuff that we're going to deal with today is negative 320 degrees Fahrenheit, and that's cold even for Vermont. And scientists use cold as a tool to let us do things and study things. So I've got a pretty big balloon here, and I've got a small container here that's a little cold. Who thinks I can fit this entire balloon inside this container?
No way.
A couple of hands going up. I'm here, right? So I'm going to put this balloon in, and what do you notice is happening to my balloon? It's just a container, but as it goes in, the balloon is getting smaller. Maybe it's all going to fit? That giant balloon? Now my balloon is still there, and it's cold, and as it warms up, it starts to look like my balloon again.
That's cool.
And you can see some of the ice coming off. So while this one warms up, I'm going to try and do another one with the other hand. So that giant balloon fit in there because as we get it cold, and I'm using liquid nitrogen, I'll talk more about that, but as we get it cold, things change. And this is why scientists like to change temperature on things, because it gives us this effect. We can take something big and make it small, make it change a bit. And so let me show you some liquid nitrogen. We keep it in special containers that are like really good thermoses, better than a Yeti. And it looks kind of like water, but it's a lot colder. And what you're seeing there, the fog coming off the top, is actually water vapor that we're condensing from the air. So we're making fog. And room temperature is boiling hot to this stuff. And so when I pour it into a fresh container, you can see it vigorously boil there. And now I have another container, an empty glass tube, a really big test tube. And I'm going to put that in there, in the really cold part. And note that the mouth is well above the liquid. So none of the liquid down here is boiling up and getting into there. We're just going to let that sit there for a little bit. And I have the same stuff, the same liquid nitrogen. going to try and get the same amount of liquid nitrogen in both. Let's see how I did. Vigorously boiling, because that room temperature stuff seemed pretty warm to these. A little more over here. Now, both of these containers have liquid nitrogen. And you can see they both kind of settled down. And I'm going to take two objects that have been sitting at room temperature the entire time, and we'll put them in. Now I'm adding room temperature, which remember is boiling hot to liquid nitrogen. So one goes in here, and one goes in here, and we'll see how long they can make that liquid nitrogen boil. Oh, and let's look back at our ice cubes. I see a little bit of water on this one. This was the one that they said felt cooler, but my ice cube is melting. Why would my ice cube melt on the one that felt colder compared to the one that felt hotter? Do you have an idea?
I think it melted colder because I think the ice cube was a bit hot.
The ice cube got hot. That's how we melt ice cubes. So everybody take a deep breath in. Let's do that again, but this time put your hand right in front of your face. Your breath is warm because you're warm. Most of you are at about 98 degrees Fahrenheit, which is warmer than the room at about 70 degrees Fahrenheit. And so if I let you touch something that conducts heat, conducts your thermal energy away from you, it feels cold. And if I give you something that's insulating, it feels warm. But if I put a colder than the room thing on something that can conduct heat well, it takes the room's heat and it dumps it into the ice cube really fast. And if I take something that's insulating, that felt warm to you, it doesn't let the heat flow into the ice cube. And so this ice cube will stay there even though this plate felt warm to my junior scientist. Now let's come back and look at these. And I noticed that I have a lot less nitrogen in this jar, even though they started at the same point. They were the same size, they were the same temperature, but I boiled more nitrogen with my metal ball because there was more stuff there. It had more matter and more thermal energy, even though it was at the same temperature. All right, got just a couple more things that I want to share with you, and one of them is playing music. So I'm going to pour my liquid nitrogen in this dewar, and I have two bells, and these bells are made out of lead. And let's listen to them. Is that a good bell? Lead doesn't make a very good bell. Lead is a really soft metal. But do the bells sound the same at least? Pretty close. So let's take just one of my bells, and I'm going to cool that bell in liquid nitrogen. I'm letting it get really cold, and I'm doing a control. So as a scientist, I have one that I'm not changing, and I have a different one that I'm changing. I'm doing something new with. And so we'll see, well, we'll hear whether or not that has an effect on our lead bell. So the lead bell is going to get just a little tiny bit smaller, because when we cool metal, it gets tinier. And here's the sound of my old lead bell, my room temperature lead bell. Not loving it. But let's try the cold one. You hear the difference? We made the lead harder. We made the lead more like glass, and it rings more like what we think of as a regular bell by virtue of getting it colder. And this is why scientists will go to the Cold Atom Laboratory on the International Space Station, as we describe over there, to talk about all the different ways and learn about the different ways that just changing the temperature can affect how much there is, or how much space something takes up in its other properties. All right. Everyone is hopefully familiar with flowers, and they're soft. We had lead, which starts pretty hard, and then we cooled it, and it got harder. So if I take flowers and put them in liquid nitrogen, we'd expect the flowers to be not as soft anymore. So as they sit there and cool, if I have regular flowers that are still warm, I can accidentally bump them against something and they're just fine. What do you think is going to happen to these flowers? So the properties of materials, how brittle, how hard, all of these effects can change as the temperature changes. And so my once soft and delicate flower becomes a little more brittle when it gets cold. Now, we've done some pretty weird things here, but this is just nitrogen that's very cold. We breathe nitrogen whenever we breathe air. Most of air that we breathe is actually nitrogen. And so the nitrogen is not the dangerous part here, the cold is the dangerous part here. But as you study more, as you learn more, as you figure out what you can do safely, and if you've been in school until 24th grade, you can be a good Vermonter. Thank you very much for coming out to see the show. There's a bunch more hands-on activities that you can do over there, where you can get a little bit closer and ask more questions. I'll also take questions if you want to come up and talk to me about anything you saw.